In this video, we'll discuss how to define the inverse trigonometric functions. In particular, we'll quickly review the basic idea of inverse functions, as well as provide formal definitions for the inverse sine, inverse cosine, and inverse tangent functions, along with their respective ranges. In this video, we're going to introduce the inverse trigonometric functions, and in particular, we're going to define the inverse sine, the inverse cosine, and the inverse tangent functions. So recall that the inverse of a function f of x is a function f inverse of x, denoted with a -1 as an exponent, with the property that when we compose f and f inverse in either order, we always get the function x back. So f inverse of f of x equals x, and f of f inverse of x equals x. If we interpret this definition in a slightly different way, another way to think of this relationship between f and f inverse is that if f of a is equal to b, then f inverse of b is equal to a. So in this sense, the inverse function undoes what the function, the original function f, actually does. It'll undo that operation. So in the case of trig functions, we know from our experience that trig functions take as their input some angle measure, whether it be degrees or radians. It takes an angle measure and it outputs a ratio. And if it's an acute angle, then it will give us a direct ratio of two sides of a triangle. And if it's not an acute angle, then there's a triangle in the appropriate quadrant that can be formed where the trig function gives us the ratio of sides with possible negative signs involved. The inverse trig functions, on the other hand, will undo this. So the inverse trig functions, when we define these will take as their inputs a ratio or a number of some kind and output an angle with that particular trig ratio. However, one of our first problems that we encounter is that given a certain trig ratio, for example 1/2, there's actually multiple angles whose sine is equal to 1/2. And so we have to come up with a restricted domain for our trig function in order to even define an inverse trig function. In order to determine if a function has an inverse or not, we use the horizontal line test, which you might recall says that the function f will have an inverse if and only if no horizontal line will intersect that graph of f more than once. So if the function has this property where no horizontal line intersects the graph more than once, then the function will have an inverse. If there is a horizontal line that touches the graph more than once, then the function will not have an inverse. Here's the graph of f of x equals sine of x. And as you can see, this function in general does not have an inverse. For example, if I draw a horizontal line here, we can see that this horizontal line will actually intersect this graph much more than once, but actually infinitely many times as we go from left to right. And so we want to restrict our domain of our function so that every horizontal line will hit the graph at most once. And one way we can do that, in the standard way that this is done for inverse sine, is to look at the function starting at x equals -pi/2 and going to pi/2. So just this stretch here highlighted in red. And now if we focus solely on that part of the graph, every horizontal line is going to intersect that part of the graph at most once. We're not going to be able to draw a horizontal line that hits the red portion of this graph twice. And so we're going to focus our attention with inverse sine. We're going to focus on the interval from -pi/2 to +pi/2, including the two endpoints. So this leads us to our formal definition for the inverse sine function, which is also sometimes called the arcsine function. You can see here there's two notations for this. We have y equals inverse sine using the standard inverse notation with the -1 exponent. Or we have the arcsine. This is a new notation that means the same thing, but this is often used because the -1 exponent sometimes also refers to the reciprocal, which is not what is happening here. So these two notations are interchangeable. In either case, the inverse sine function or the arcsine function is defined to be a function whose domain is the closed interval -1 to 1, and has range closed interval -π/2 to π/2, defined by this rule here in red, that y equals the inverse sine of x if and only if the sine of y equals x. So in other words, it undoes what the sine function does. In this case, we have sine of y equals x, so we have y as some angle, the sine of it is x, and the inverse sine takes as its input that value x and outputs the angle y. So a quick way to summarize all of this is by saying that y is going to equal the inverse sine of x, or y equals arcsine of x. These are, again, the same notation. This is going to happen exactly when the following two things happen: when the sine of y is equal to x, and when the number y is between -π/2 and π/2. So all I've really added in the blue is I've added in the range, the fact that the inverse sine must be in this range of -π/2 to π/2. So if we ever have a problem involving inverse sine and we come up with an angle which is either bigger than π/2 or smaller than -π/2, we know we've done something wrong. Right? By definition, the inverse sine of any number x will always be between -π/2 and +π/2. We could approach the inverse cosine function in a similar manner. Here we see the graph of the function y equals cosine of x. And again, as we saw with the sine function, the entire function does not have an inverse because a horizontal line like this one here will intersect this graph over and over and over again. And so that's not going to work. So we need to do the same idea as before, is to restrict the domain of the cosine function and only focus on one portion of the function. If we try to do the same thing as sine, going from -π/2 to +π/2, if we try that same restriction, we see that this still doesn't actually help us, because this particular region of the graph still has horizontal lines that intersect it more than once, and so this graph still fails the horizontal line test. And so that portion there isn't going to work. And the standard portion that does work is the portion from x equals 0 to x equals pi. And when we look at that region of the graph, we notice that any horizontal line will hit this graph at most once. So for inverse cosine, we want to restrict our domain of the cosine function from 0 to pi and look at the inverse function on that domain. So the formal definition for the inverse cosine function, or the arccosine function, looks almost identical to the inverse sine with one significant difference. Again, the idea is that we have a function whose domain is -1 to 1, and in this case the range, this is the difference, the range is now 0 to pi, including the two endpoints. And the rule is exactly the same with cosine in place of sine. Y equals inverse cosine of x means that the cosine of y is equal to x. So in other words, if y is some angle whose cosine is x, as long as y is in the range 0 to pi, then the inverse cosine of x is equal to that angle y. And again, here at the bottom in blue, we see a way we can summarize the rule by putting the range in with this algebraic rule, so that the y equals inverse cosine of x, or y equals arccosine of x, means these two things. It means the cosine of y is equal to x, and also that y is somewhere between 0 and pi perhaps including the two endpoints. And again, if we have an arccosine or inverse cosine problem and we get a value that is either bigger than pi or smaller than 0, then we know that we've done something incorrectly, because that would violate the range in this definition of inverse cosine. The last inverse trig function we're going to define is the inverse tangent. So here we see the graph of y equals tangent of x. And in this case, it's a little bit easier perhaps to see how we are going to restrict our domain. We know the tangent graph consists of a bunch of branches. Here we can see 3 of them that are disconnected. And all of them individually have an inverse. So we just pick the one that goes through the y-axis, which is the one right here. And like with our restrictions for inverse sine and inverse cosine, we see that any horizontal line we draw here will intersect this graph at most once. So this branch of the tangent function, even though it goes all the way down as far as we want and all the way up as far as we want, this graph will never violate the horizontal line test, and so this portion has an inverse. And so as we can see here, we're focusing on the region between negative pi over 2 and pi over 2 without including the endpoints. The tangent function is not defined at pi over 2 or negative pi over 2, and so we cannot use brackets on this interval like we did with the inverse sine. So formally, the inverse tangent or arctangent function is defined to be the function whose domain is negative infinity to infinity and the range from negative pi over 2 to pi over 2, but the open interval, not including either of the endpoints, defined by the standard inverse rule that y equals inverse tangent of x if and only if tangent of y equals x. We can summarize all of this as we have for the inverse sine and inverse cosine functions as in blue at the bottom, to say that the y equals inverse tangent x or y equals arctangent of x means that tangent of y equals x and y lives between negative pi over 2 and pi over 2. So here's a quick summary of the 3 inverse trig functions that we've defined in this video. Notice that all 3 of them are defined using standard inverse function rules. That is, that y and x are interchanged, that the inverse function will undo the original function. The big differences here are the 3 ranges for the inverse trig functions. So inverse sine is defined to be the value between negative pi over 2 and pi over 2, including the endpoints. Inverse cosine is defined to be the value between 0 and pi, including the endpoints. And the inverse tangent is defined to be the value between negative pi over 2 and pi over 2, not including the endpoints. And so in addition to finding an angle whose sine, cosine, or tangent is the given value, we need to also respect these particular ranges and make sure that the values that we give for inverse sine, inverse cosine, and inverse tangent fall within the appropriate intervals indicated here.